Hello, everybody. Today I thought I was gonna have some fun, and I will record it, just to share the fun. So don't expect that at the end of this video you're gonna get some fancy new library or, I guess, some mind-blowing teachings, but I hope you learn something, and especially that I do. What I was gonna do today was play a little bit with the Swift runtime, especially with the concurrency runtime. So that means we need to write some code, run it, and try to debug it and see what's going on under the hood. So to start, we're just gonna start with, I don't know, we can do a task group of, I don't care, of the output. And here we have a group, and we are now able to span child tasks to see how everything behaves. So the first thing to understand about the Swift concurrency runtime is that there are kind of two big walls, right? One of them is everything that runs on the main actor. And for that, we can do something like a prof, which is something I always like to do. Because then when you have a function that it's, on the main actor, you can try to do prof +1, and the compiler is going to tell you, whoa, you are not on the main actor, because if we check for on the prof, you can see that it's main actor. But the point is now you can go here and say, okay, you're main actor, and the prof compiles. So what can we do here? So let's start with just some busy work. And just to see it, we can say we're printing on main, and we're printing that value. That's it, nothing else. So we're gonna start by spawning a new child task and just, calling on main. And if we run this, we're gonna see through this session that Xcode sort of freaks out a little bit, it doesn't like that we're keeping everything busy all the time, right? So see, the first time it printed, it was already on the tens of thousands. But the point is, we can pause and we can see, well, all the prints, but most importantly, we can see here on the left how we have the main actor that it's busy. It's keeping busy the main thread running this on main function. So that's what I wanted to see. And we have this other thread here, but it's, it's a weird thread. It's a weird thread. I'm still not sure what they do, but they show up on every program. So we can ignore them for now. But let's continue. What else can we do? Let's keep some function that does also some busy work. Yeah, let's do some busy work. And we're going to change it here just so we know. And just to make things even more obvious, just to see how the runtime behaves even, at the extremes, let's pass a parameter here. So you can distinguish between different calls to this function. And just to, prove the point again, if we cannot access the prof here, so it means we're not on the main actor. That's good. So let's add another task, and here we're gonna call busy. The difference now is that we're gonna run this in a big for loop. I don't know, from 100,000, something like that. And we can pass the number here just to distinguish them. And of course, we need to call await. So if we run this now, besides Xcode freaking out a little bit, we're gonna see how, well, again, Xcode, see, it slows down and everything, but we can pause it. Okay, that's what we want to see. Cool. So first of all, if we look at the log, we see we're printing busy, and we're busy number 2. And again, we're spawning so many, and it just got time to go to number 2, but you saw how many it printed, right? How many iterations? Oh, but we see 6, 7. Yes, see, so we already see how things are running concurrently, one after the other, but we don't see many calls to busy with big numbers coming from here, right? So that starts telling us something. And if we're lucky, don't we see a main somewhere? Yeah, there you go. So you can see main here also. Cool. But most importantly, let's look at now how the threads look. So we still have the thread 1, which is the main thread, a serial thread that runs on main. So main runs the code that runs on the main actor. Nothing new. But now we can see how we have all these threads, and there is a few, that if we look at the description, they all say cooperative, concurrent. So this is the other part of, I guess, the threads behind Swift concurrency. So first we see the main thread, and the main thread, well, it obviously runs the code that it's linked into the main actor. So code that runs on the main actor isolation context, it runs on the main thread, the thread one. But then we have all these threads here with all this curious name, cooperative. So this is the Swift Concurrency Runtime cooperative pool of threads that are all concurrent, and it's cooperative. So like this is shared across the entire Swift Concurrency Runtime. So you don't put anything specifically on one of these threads. You don't put it on the main actor, for example, and then they all end up here. So we can see how busy it's running on thread 5, and we can even see the instance of busy. In this case, the third call we did. If we go here, we'll probably see the first call we did, and so on and so forth. The point I wanted to articulate here is how, because we're keeping all the threads busy, we are not cooperating, right? And that's one of the big topics with this style of concurrency, that you need to be cooperative. Otherwise, you're gonna mess not only your code but the entire systems. Because of that, we just see that the cooperative pool had to spawn all the threads it's defined to have available. Even that was not enough, because we only started processing 7 calls, right, to this busy function, and that's because it's all a little bit busy. We're not cooperating. Okay, so we have these two kind of walls, right? One is the cooperative pool, the concurrent pool, and the other is just the main thread. But I wrote a post about this interesting parameter that you can pass as an environment variable. So what this parameter does is actually limits this cooperative pool to only have one thread. So at maximum, it's always gonna spawn only one thread. But that's, again, for the cooperative pool, not in general. So if we pause, first of all, if we take a look at the logs again, we see how, well, main is doing its own thing, but how busy it only was able to run the 0, the first call that we did, right? And if we look at the threads, now we see how we only have one extra thread for the cooperative pool. It's only thread 2. Again, thread 1, it's still for the main actor, and exclusively for that. We can go here and we can see how it's running still the main actor code, but now the thread 2, it's running busy and nothing else. There are no more threads, right? So we have told the concurrency runtime to only run with one thread on the cooperative pool. It's not gonna spawn more threads than that. Of course, I don't recommend that for production, but it's very interesting to understand what's going on. So this exploration is a little bit curious for me, because one of the things I always do when I try to teach Swift concurrency, it's something that I repeat over and over and over, which is forget about the threads. Even more, forget about everything you knew about concurrency beforehand. Because the more of a blank slate you have, the easier are things, honestly. Like, I've seen people understand way easier Swift concurrency when they don't have any baggage. And, people with experience struggle because it's sometimes tricky to accept the change and to leave things behind. One of the things I always say is stop thinking about threads. Just think about isolation domains and, making sure you put suspension points and all that stuff, but don't think about the threads. Well, of course, in this video, we're talking about threads. So, I find it kind of funny today. So the reason I never want to talk about threads, it's because in theory, you should be able to write your Swift concurrency code. Just put async here, the isolations in there, and everything should be able to run on your MacBook, on your iPhone, on a server, on the watch, but also on more constrained environments where you could imagine that there is only one thread available for your entire program. Is that what we did? No, because we still had one thread for the main actor and another thread for the cooperative pool. As far as I know, there is no way to tell the runtime only use one thread. But in Swift 6, we have some new tricks that we can employ. So we have this task executor preference, right? Which we tell it a task executor, and then we can put some code inside. In this case, I'm just gonna put the entire task group, and because we're using Swift structured concurrency, I'm not spawning any new tasks, only child tasks. The preference for the task executor is gonna be respected. Of course, this is not a foolproof system, because any code inside the call stack can override the task executor again, right? But for this scenario and for playing a little bit with this runtime, it's very useful. Of course, we need an await here. And now what will we put? So the executor, well, we have one executor, which is the global concurrent executor. And that's what it's there by default, right? That's the executor we have been working with and the one that I've sort of explained. You can read a little bit more about it here. By default, it uses a fixed size pool of threads and should not be used for blocking operations. We already proved that when you do blocking operations, things don't work as expected, right? We actually want to put everything that should go on the global concurrent executor on the main thread. So how we do that? So we can make our main executor, and we can conform to this task executor protocol. We just need to implement this enqueue function, which gives us a job. I mean, forget about the type, we don't have to get there, but just this is a job, right? And that's what executes your code, basically. It's your code, actually. So we need to enqueue it for execution. Where do we enqueue it? Well, we're piggybacking into the main actor shared instance and just calling enqueue in there, and there you have it. Let's get here, let's try to pass it here and see if this works. Okay, so we saw how we only printing main, which is fine, and main is on the main, but that doesn't help us. Let's try to run it again, see if the behavior changes a little bit. And let's pause. No, it's still there. Okay. No, I'm not. I guess I'm just unlucky. Maybe if we try to spawn them first. That's what happens when you play with the runtime at this level, that things are not deterministic in a way. So depending on what you want to prove, gets tricky. But okay, I think changing the order did the trick. So we can pause and see. So okay, so now we're just printing busy, the freeze call to busy. Yeah, I think nothing else was able to run. On other calls, things were different, but let's just run with it. Look at here, busy, but on the main thread. And again, this is running on the main thread, but it's not on the main actor isolation. See? It's not on main actor isolation. It cannot access things from the main actor, but at the executor level, it's running actually on the main thread. And since we are keeping that thread busy, it actually means that there is no way for the code on the main actor to ever run, which is obviously bad, but that's why we're having some fun today. So what else? What can we do? Try to be a little bit nicer, right? So we can say if I is multiple of 10, so every 10, let's do a yield. So yield will give back the execution. It's sort of suspending the current task and giving back the execution to the runtime in order for it to have a chance to run other tasks, right? So it's like we're trying to be nice. It's like, okay, please run other task if you want. Again, it's not 100% sure that it will, because it depends on the priorities and stuff like that. But for what we want here, it should actually do what we want. So let's try it. Run again. See if we can see a difference behavior that helps us understand a little bit more how this runtime works. Okay, we can pause. We still see the same thing. Main thread is actually running the busy function. But now I hope that if we can go here, yeah, see? So the main actor started running, and when it reached 10, it gave a chance to another task to run, which in this case was the first one from busy, and then that one gave a chance to another one. So they sort of intercalate every 10, and we can see how the different busy calls go up, you see, but you see how at each individual busy execution, basically the Y number in the loop doesn't go that high, because again, every time we give time to another task to execute. And in theory, and actually we can try that. If we reduce the number of calls to busy, let's just say, I don't know, let's just put 10. We should see how actually the main actor has again another chance to run. Of course, with hundreds of thousands, the chance is going to be very slim, especially if after 10 iterations you sleep again. But in theory, So if we search for main here, we can see how it did 10, then it switched, but it came back again. Yeah, exactly. After 10 executions from the busy function. So it's sort of like they are sorted in a fifth order. And then it goes on the same order again. Makes sense. Makes sense. That's good. That's good. So that's something new we now understand. So no big revelation, right? But I like playing with these things because it helps me understand a little bit more how things work behind the scenes. And hopefully not have to rely on any of these, because that's the whole point, but still keeping it in mind. We see here how we just wrote normal looking async code. It was able to run on the default configuration for this MacBook, which was like a lot of cooperative pool threads and the main actor thread, right? But also I've been able to trick it. So you could imagine that maybe this trick was not part of me playing, but actually I took this code and I ran it on a different hardware where only one thread was available, right? So sort of what, JavaScript does every day, which they only have one thread available on normal code. But the point is, I didn't have to change anything else, right? I didn't reshape my code. I added this just to illustrate that if you don't cooperate, things are not working as you want. But usually you don't write this code that keeps the thread block, right? We always call something that it's gonna wait at some point and it's gonna actually suspend the current task. So usually if you write normal, acceptable Swift concurrency code, you don't have to worry about it. And this sort of proof that it should be able to run in a different environment where there's only one main thread. So that's cool. Is there anything else I want to try? Yeah, so since I have this setup here, I thought I will give it a try doing something slightly different with async streams. So let's, for example, make a produce function. Well, let's make the stream here. So let's make a stream. And I'm going to make a stream with this function that gives me the stream. I think that's the order and the continuation. Okay. And this is going to be an async stream, make stream. There you go. I think I need to give you the type, right? Yeah. Whatever. Let's just keep it simple. So now what if I start awaiting the numbers in the stream, because this is a stream of integers, so it should give me integers here. And I can print here, for example, stream n, and let's leave it like that. Okay. But now I need to produce this, right? So I'm gonna, in a separate child task, I'm gonna call, yeah, there you go. I'm gonna call this produce. And I'm gonna pass the continuation. And this should be an async stream of in continuation. So now we have basically a producer consumer scenario. This is running on the main actor only. So that's so I can exercise this specific scenario because I'm curious about what's the behavior of the continuation when you're on this sort of environment. So here, I guess I'm just gonna, again, do my very simple trick of spawning, of iterating a lot of times. Let me give you my mental process that I'm going through. So we know that the Swift Concurrency Runtime, it sort demands cooperation for you, basically, for the different tasks that it runs. We saw how if we didn't yield at any point, if we kept just our code busy, the runtime never had a chance to actually change to another task, right? So it means that we're blocking the execution and nothing else will be able to run. And in this original case, it was sort of fine, right? Because everything was independent. Like we're just iterating here and printing, we're also iterating here and printing, but they don't depend on each other. But when we use an async stream, there's sort of a, yeah, no, it's not sort of, there is a dependency here, right? Like we have a task here that it's producing data, another task here that it's consuming that data. So there is a dependency between two tasks. And I want to see what happens if these tasks that are producing and consuming, they don't behave, right? They don't behave as expected and they don't cooperate. That's a keyword here. So in this case, I'm not cooperating. right? So maybe we can just remove this for now, just avoid more complication, but I'm gonna keep this one just to make sure the main thread, the only thread we have, is busy. So if I run this, let's see what happens. My expectation is that the producer is gonna execute, start this for loop, and start producing, but at no point it's gonna be consumed. That's my expectation. And the reason is because there is no await, right? So there is no await here. So yield, yeah, that's interesting, right? Because there is no await. So even if you think you're yielding, okay, is the main actor being too busy? No, we see how. Well, I see the streams here, but I also see the main, and I waited a lot. Let me see. There you go. So how many times I iterated? Yeah, I iterated a bunch of times. But you can see, there you go. Yeah. So, I mean, we can sort of ignore the main, because that's just the same loop as before, that actually stops every 10. But anyway, at the first chance that the runtime had to schedule this produce call, it did. Right? And you can see how it's before and after. Every iteration is calling before and after, which means that from the async stream point of view, the producer is actually giving values. It's actually yielding into the async stream continuation. And we can see how it's doing it one after the other, giving values and giving values to the stream, but it doesn't give a chance to the consumer to actually read them. And this is gonna go for a long time, you see, because I set 100,000, and then it finishes the 100,000, which they should be over here. There you go. And then, well, the main actor had a chance to run again, and then the stream, and it takes the freeze value after the producer produced 100,000 elements. For the first time, the consumer, this piece of code here, was able to iterate first to take that first value. And then, because the for await, and that's all because the for await, it's a suspension point. So basically, this confirms my mental model. And that's sort of my goal here. So my mental model is the cooperative runtime only is able to switch tasks in suspension points, or what's more technically a potential suspension point, which is when we see the await keyword, which is very powerful because it means that reading your code, you can immediately know where suspensions are going to happen. And that's honestly very important because other languages don't do it, and it's a mess. Honestly, it's a big mess. But anyway, that's another conversation. Going back to this, it means that the producer is running for a long time, just giving values to the continuation and yielding. Yeah, you're yielding the value, but you are not actually yielding to the concurrency runtime, which doesn't have a chance to run the consumer. After many iterations happen, even after the main actor had a chance to run again and suspend, then you receive the freeze one. And because at every iteration there is a potential suspension point, there is an await, it means the main actor still has a chance to run between the for loops on this consumer. And then in this case, again, it's not 100% deterministic, which means that it was able to iterate 2 times on the consumer side before the main actor ran again. But that doesn't matter. The point is, there is no wait here. It means this suspends and the runtime is able to schedule something else, but there is no await here. Even if we have a continuation yield, this is an async stream continuation, right? It's not really a runtime continuation where we can suspend directly. So that's actually very important and interesting. Yeah. I guess the conclusion is be careful when you do this. Because of course, in a normal scenario, there is probably gonna be another thread running the consumer, which means that as you feed the data, the consumer is gonna consume the data. But you cannot rely on that. You cannot rely. I proved this, I changed how the runtime behaves, and now the code, you could say it's broken, right? If this data was bigger or it was infinite or whatever, there is no way that the consumer will be able to keep up with this. So that's interesting. So that means that what you want is, just in case, to just put some sort of yield here. And maybe we could do the same that we did here. Every time you fill the async stream with 10 values, give the time give a chance to the consumer to actually consume these values. Let's run it and see if actually that works. So we still haven't yielded all the possible values, but the question is, so I see the main thread. There you go. So you see, so we're yielding 559,000 and we are consuming 5,000. Not deterministic, but at least we are giving a chance to the consumer to actually consume something. I guess in theory, if we just do it every time, it will be more balanced. In a way, we give more work to the runtime to actually switch the tasks. But assuming that's kind of fast, maybe there is no harm on yielding so much. Yeah, see? So we're yielding this value and we are consuming the previous one, basically. So yeah, again, it's not 100% deterministic. So there could be that the async stream is buffering more than one, but overall, it's better than before. We're actually giving a chance. And it's all about that, right? It's like, let's cooperate. I'm giving the runtime the chance so you can consume the value. Cool. So I think that's everything I wanted to play with today. Sort of a weird video, and I know not, many people doesn't like this, but I really, really enjoy seeing other people code and other people think and see how they go through things. So I thought, I'm gonna spend a while playing with the runtime. Why not record it? Maybe somebody else actually enjoys it as much as I do. So just to recap, main actor, main thread, everything else goes into the cooperative pool by default. And this cooperative pool grows into a certain number of threads. But in theory, everything you write with Swift Concurrency should be able to run in other environments with less resources. And that's what we sort of prove today with this our main executor. Or at least not proof, but convince myself that I understand how the runtime appears to work, and more importantly, how important are the suspension points and how they play together with a producer-consumer strategy with an async stream. I'm sure there is more to learn. I'm sure there are many mistakes I've done, but so far my mental model stands. So I'm happy with it. So I think we can leave it here. Thank you for watching and see you all next time, I guess.